Hi, welcome. Let's continue with how images are formed. Not all reflecting surfaces are going to give a clear and well-defined image. There can be losses in the path, light can be absorbed, or light can be diffused and scattered by inhomogeneous media. But also not all points reflected off of the surface are going to meet a specific image point. The image can be blurred. This is what we call aberration. Surfaces that form perfect images are called Cartesian surfaces. Only conical surfaces are going to deliver a neat image. In 3D, they would be an ellipsoid, hyperboloid, or paraboloid, or spherical surfaces. Because of ease of fabrication and therefore abundance, we are going to study spherical lenses. Let's consider a spherical concave mirror. Concave means that the center of the mirror is at the same side as the object. Let's define the angles and distances in this drawing. We have one ray going along the axis and reflected back along the axis. We have another ray going to point N and being reflected to a point I. C is the center of the curvature of the sphere. Following the law of reflection, we know that these two angles are the same, theta. V is the vertex, which is the intersection between the axis and the mirror. O is the distance from the vertex to the object. I is the distance from the vertex to the image. R is the radius of curvature of the spherical lens, the distance from the vertex to the center C. Let's do some trigonometry with the angles now. The sum of the angles of any triangle is 2 pi. For the first triangle, we have that alpha plus 2 theta plus phi is equal to pi over 2. From this second triangle, we also know that delta plus phi is equals to pi over 2. Combining these two results, we get that delta is equal to 2 theta plus alpha. If we do the same for this third triangle, and we combine with previous results, we get that beta is equals to theta plus alpha. Take a moment to verify it. We now can combine these two equations as delta plus alpha equal to 2 beta. Now is when we have to make an approximation. We're going to find the so-called mirror equation, but it's only valid for small angles, but works most of the times. This is paraxial optics if the angles are small. So we can approximate the angles by the tangents. Alpha by tangent of alpha, beta by tangent of beta, and delta by tangent of delta. From the figure, the tangent of delta is, in the small angle approximation, h over I. Tangent of alpha is h over O, and tangent of beta is h over R. This gives us the following equation that relates the positions of the object and the image with the curvature of the mirror. This is the mirror equation. Now we need to introduce certain convention of signs. As for positions of objects and images, O's and I's, if they are real, those distances will be positive, and if they are virtual, they will be negative. As for the curvature of the mirrors, if the mirror is convex, R will be positive. If the mirror is concave, R is negative. In the present example, R is negative, while O and I are positive. This requires us to fix by hand the equation and add this negative sign here. Now, because the focal point of the lens is of special interest, allow me to write this mirror equation in terms of f, being f the focal distance, or the distance from the vertex to the focal point. rays coming from infinity will reflect and pass through the focal point. Because an object placed at infinity means that this fraction is 0, I get that the focal point is minus r over 2. This will be the positive for a convex mirror and negative for a concave mirror. I define f as negative r over 2, and then I can write the mirror equation as 1 over O plus 1 over I equal to 1 over f. Let me now introduce a more extended notation. S be the position of the object and S prime the position of the image. 1 over S plus 1 over S prime equal to 1 over f. Look that this equation is symmetric in the positions of the object and image. This means that those points are conjugate points. This is in agreement with the reversibility of light rays. This equation, because of the definition of focal distance, is valid for concave and convex mirrors. In both cases, f is positive. Another interesting magnitude is the magnification, m, of the lens, by how much the image magnifies or reduces an object. We define it as h sub I over h sub O, which, looking at these similar triangles, we find that the magnification can also be written as negative S prime over S. Here we have introduced the negative sign so that when the image is oriented as the object, the magnification is positive, and when the image is inverted, the magnification is negative. This is very convenient because we can calculate the magnification of a mirror just by the characteristics of the mirror, not needing to take any measurement. For a plane mirror, r is at infinity, so the focal point of a plane mirror is at infinity too. Then, from the mirror equation, we have that S is negative S prime and the magnification is 1. May the science be with you.